Hello everyone, this is lecture 15, optimization of discrete model. In this lecture, we're going to look at the optimization problems for discrete models. We kind of have seen this problem before a few lectures ago when we talk about curve fitting criterion. One of the particular criteria that we look at is Chebyshev criterion. So this criterion say that given a collection of n data points of the form x sub I, y sub I, you want to fit this collection to the line of the form y equal to ix plus b that minimize the greatest distance between any data point and the corresponding point that you find on the line. Right. Another way to word this is to use the following formulations. That is the largest absolute deviations or the residual or the maximum of the absolute deviation is minimized over the entire collections of data points. All right, so this criterion defines the optimization problem as follows, right? You want to minimize R, right? The optimization is either you want to minimize something or you want to maximize something. And to minimize this particular residual or the largest absolute deviations, it has to subject to certain conditions. And the conditions that we have here in this particular case is that of R minus R sub I greater than or equal to 0 and R plus R sub I greater than or equal to 0. Again, R is the residual or the maximum of the absolute deviations. For R sub I is the residual of the particular data point. All right. And in general, this problem is called the linear program. Okay, the linear is that of because everything depends linearly, right? Because we want to fit linear line to a set up data point. And more generally, we have the optimization modeling. The framework for this type of problem has to form. The first is that you want to optimize certain functions, right? And this functions has, or the optimization process has to depend on certain conditions. And usually we call the conditions constraints. All right, so let me clarify some wording here in this particular framework. All right, so the word optimize, when you use optimize, that means you want to minimize or maximize. So means minimize or maximize. All right, so this notations exported face letter with the arrow on top is called vector, right? So that means there are multiple components in this particular variable. And this variable is called the decisions variable of the model. Right, so there is multiple component in X. All right, and the functions f sub j of X means the objective functions, right? Now, this objective function depends on the problem that you're working with. So, for example, you want to maximize a profit of some bank account, right? You want to maximize the profit of some company when they try to produce certain product. So this is the objective functions, right? We're going to do some example a little bit later so that you understand what type of objective functions we can come up with, right? Again, depends on the problem that we have. And in this case, you have the subscript J, right? So subscript J, this indicates that there may be one or more functions to optimize. Right. And the last wording in this particular framework is subject to, that indicates a certain side conditions must be met. Right, so indicates certain side condition must be met. All right. And these side conditions can be classified into two groups. It's either called the unconstrained optimization problem or constrained optimization problem, right? So for unconstrained, it means there's no constraint or no side conditions. So no constraint or no side condition. And constraint optimization problem is that one or more side conditions are present. All right. So that's it for the framework. The idea is that can you formalize the discrete problem given to you, right? What are the objective functions that you want to optimize and based on what particular conditions. All right, so that's what we're going to do in the next few examples, right? So in the next few examples, we're going to have some problem related to probably kind of the real world situations where you have to come up with the objective functions. Either you want to minimize that objective functions or maximize that objective functions, and you have to do this based on certain conditions. All right, so let's take a look at the first example here. So in this example, we have the diet model, right? So a list of available foods is given together with the nutrition content and the cost per unit weight of each food. So a certain amount of each nutrition is required per day. For example, here's the data corresponding to a civilization with just 2 types of grain, right? Just G1 and G2, and 3 types of nutrition, starch, proteins, and vitamins. So obviously it's not really the real world situation, but it's kind of related to the real world situation because in reality, we have more than just 3 types of nutritions, right? But to, of course, minimize the process of our optimization problem, we just choose to have 3 different nutritions. All right. So the requirement per day of starch, proteins, and vitamin is 8, 15, and 3 respectively. So the problem is to find how much of each food to consume per day so as to get the required amount per day for each nutrition at the minimal cost, right? So we want to minimize the cost, right, obviously. And this optimization process has to depend on certain conditions that the requirement per day of starch, proteins, and vitamin is 8, 15, and 3 respectively. All right, so let's formalize this particular optimization problem. All right, so first I'm gonna let x1 to be number of unit of grain G1 to be consumed per day. And x2 is going to be the number of unit of grain G2, so grain G2 to be consumed per day, right? So you have two type of grains here. Now let's come up with the objective functions. Again, in this case, given from the problem, we want to minimize the cost, right? All right, so the objective functions or in other words, the objective function is the function to be minimized in this particular case. In other case, that is the function to be maximized, maybe, right? So we want to minimize the cost, right? So you come up with the function f of x1, x2, right? And this is equal to 0.6 times x1 plus 0.35 times x2, right? Because that's going to be the cost per kilogram, right? Or the amount of dollar per kilogram. And it depends on the number of unit of grain G to be consumed per day. And grain G consists of three nutritions, starch, proteins, and vitamins. Okay, so that is the objective function. We want to minimize the cost. Okay. So based on what conditions though? All right. So we want to minimize this function based on the following constraint. So we're going to come up with the constraints. Right, so the constraint is that right off the bat, you need to assume that x1 and x2 has to be greater than or equal to 0. X1 and x2 cannot be a negative number because that is the number of unit of grain that you need to consume, right? You either don't consume anything or consume a positive amount of grain or a positive amount of food. So x1 greater than or equal to 0 and x2 greater than or equal to 0. Right, so that is only non-negative amount of food. All right, so that makes sense. Right. Now, moving on to different type of requirement here. So they say that the requirement per day of starch, proteins, and vitamins is 8, 15, and 3. So for starch, you have that 5x1, right? So 5x1 plus 7x2 has to be greater than or equal to 8. Okay, because of the requirement 8 here for the per day of starch. The next type of nutrition that we need to look at is proteins. So that is 4x1 plus 2x2 is greater than or equal to 15, right? Which is the requirement per day for protein. And the last one is vitamins. That is for vitamins, you have 2x1 plus 1x2 has to be greater than or equal to 3. So 2x1 plus x2 greater than or equal to 3. So this is the optimizations that optimization problem that we need to formalize. All right, so put everything together. So here's the optimization problem. So this is what we got, right? So we want to minimize the function f of x1, x2 equal to 0.6 x1 plus 0.35 x2, right? We want to minimize the cost function subject to the following conditions, right? So 5x1 plus 7x2 is greater than or equal to 8. 7x2 greater than or equal to 8. 4x1 plus 2x2 is greater than or equal to 15. 2x1 plus x2 is greater than or equal to 3. And that x1 is greater than or equal to 0 and x2 is greater than or equal to 0. So that is how you formalize an optimization problem. All right, so moving on to the next example, right? Let's try to formalize this particular problem. So suppose that a certain company manufactures 4 models of desks. In order to produce each desk, a certain amount of man hours are needed in the carpentry shop and in the finishing shop. For instance, desks of type 1 need 4 man hours, right? 4 man hours. of manufacturing in the carpentry shop and 1 man hour in the finishing shop before their production is complete. So each sold desk guarantees a certain profit to the company depending on the model, right? So for instance, the company makes $4 profit each time a desk of type 1 is sold, right? However, the number of available man hour in the carpentry shop and in the finishing shop are limiting to 6,000 and 4,000 respectively. So I make a typo here. So this should be $12 profit each time a desk is of type 1 is sold, right? So for the desk of type 1, the profit is $12. The desk type 2, the profit is $20. And for the desk of type 3, the profit is 18, and desk 4, the profit is $40. All right, so let's formulate the following optimization problem for the discrete model. All right, so what we're going to first assume is that let x1 be the number of produced unit of desk 1, right? So x1 is the number of produced unit of desk 1. Right, x2 is going to be the number of produced unit of desk 2. Right, x3 is the number of produced unit of desk 3. Right, and x4 is the number of produced unit of desk 4. All right, so what we're trying to do, of course, in reality, you want to maximize the profit that you're going to gain. Okay, so you come up with the objective functions. So in this case, you have 4 different desks, type of desk, right? So f of x1, x2, x3, x4 is going to be that of 12 times x1 plus 20 times x3, x2, sorry, plus 18 times x3 plus 40 times x4. So that is the objective functions, right? We want to maximize the profit. So 1, 2, maximize f of x1, x2, x3, and x4, right? So this is profit function. Okay, so subject to certain conditions, right? So it depends on the available man hours that you have for either in carpentry shop or in the finishing shop. Okay, so the constraint that we need to impose, right off the bat, you need to consider that x1, x2, and x3 has to be non-negative numbers because you either don't produce any desk or you have to produce a positive number of desks. All right, so x1, so the first condition is that x1 greater than or equal to 0, x2 greater than or equal to 0, so on and so forth, right? And that is the non-negative number of desks produced of each type produced. All right. Now we also take into account the number of man hours available. Okay, so that is 4x1. So here 4x1 plus 9x2 plus 7x3 plus 10x4 has to be less than or equal to 6,000 because you don't want to exist the amount of the number of hours that you have available. Okay, so 4x1 plus 9x2 plus 7x3 plus 10x4 less than or equal to 6,000. And in the finishing shop, the number of available man hours should be 4,000. So x1 plus x2 plus 3x3 plus 40x4 has to be less than or equal to 4,000. So x1 plus x2 plus 3x3 plus 40x4 has to be less than or equal to 4,000. So here's the optimization problem. Right. So we want to maximize the profit function. So maximize, let me do this, f of x1, x2, x3, x4. And the function is 12x1 plus 20x2 plus 18x3 plus 40x4. All right, subject to that 4x1 plus 9x2 plus 7x3 plus 10x4 less than or equal to 6,000, and x1 plus x2 plus 3x3 plus 40x4 less than or equal to 4,000. And at the same time, x1 has to be greater than or equal to 0. x2 is greater than or equal to 0, x3 greater than or equal to 0, and x4 is greater than or equal to 0. So that is the optimization problem for the second example. Now let's move on to the last example for this particular optimizations of discrete model. So in this example, an investor has $40,000 to invest. She is considering investments in saving at 77%, in bonds at 9%, in stocks that have been consistently averaging 14%. Because there is a varying degree of risk involving in different investment, the investor has listed the following goals for her portfolio. So she has 5 different goals here. She wants a yearly return of at least $5,000, an investment of at least $10,000 in stock. Right. An investment in stock should not exceed the combined total in bonds and saving. And the liquid saving account between $5,000 and $15,000. So this is the liquidity, the amount of cash that she has in the saving account should be 5,000 to 15,000, and the total investment must not exceed $40,000. Now, suppose the investor feels she must have the return of $5,000. We all want that, right? And must invest at least $10,000 in stock and cannot spend more than $40,000, but is willing to compromise on goal 3 and 4. So let me name this. So goal 1, goal 2, goal 3, goal 4, and goal 5. However, she wants to find a solution that minimizes the amount by which these 2 goals fail to be met, right? So let's formulate this optimization problem. So there are 5 goals, and in general, she wants to make some investment, right? So there are 3 types of investment that she can make. She can put that in the saving account, she can buy bonds, and she can buy stocks, right? And she has certain conditions that we need to follow, right? A yearly return of at least $5,000, an investment of at least $10,000 in stock, and the total investment must not exceed for $40,000. So that's the 3 goals that she said that she must have. Now, goal 3 and goal 4, she said that, okay, I can compromise that, but can we actually minimize the amount by which these 2 goals fail to meet? So that is the requirement from our investor or our customer for that matter. So before we doing any formulations, we're going to let X to be the investment in saving. Y to be the investment in bonds, and Z is the investment in stocks. All right, so we have 5 goals, right? So we're gonna list out these 5 goals in terms of mathematical inequality. So you have goal 1 is going to be that. So goal 1, a yearly return of at least $5,000. So I don't know how much I'm gonna put into saving bonds or stocks, but what I'm gonna do that I'm gonna put 7% into the investment in saving at 7%, in bond at 9%, and the return for stock is going to be 14%. So from goal 1, I have 0.07x plus 0.09y plus 0.14z has to be greater than or equal to $5,000. So instead of the percentage, I write in decimal form. Now goal 2, the second goal is that the investment of at least $5,000 in stock. So Z has to be greater than or equal to 10,000, sorry. Goal 3 is that the investment in stock should not exceed the combined total in bonds in saving. So Z has to be less than or equal to the total, the combined total of bonds in saving. The fourth goal is that the amount or the liquid saving account between $5,000 and $15,000. So this is saving. So X has to be between 5,000 and 15,000. So 5,000 less than or equal to X, and X is less than or equal to 15,000. And the last goal, goal 5, is that the summations or the total investment must not exceed $40,000. So X plus Y plus Z has to be less than or equal to $40,000. So that is the 5 constraints that we need to formulate. Now to incorporate the minimizations of the amount by which goal 3 and goal 4 fail to be met, we're gonna let or denote F3 to be the amount by which goal 3 failed to be met, and F4 to be the amount by which goal 4 failed to be met. All right, so the optimizations problem is going to be all right, so we want to minimize the amount by which goal 3 and goal 4 failed to be met, right? And subject to these 5 conditions that given to us by the investor. Okay, so subject to so I'm not gonna rewrite this inequality, but I'm gonna write a G1, G2, G3, G4, and G5. And also the conditions that we need to impose is that X, Y, and Z has to be a positive number to ensure that we have the positive amount of money that we're going to put into this account. Okay. So that's it for me for optimization problem for discrete models. So basically, we're just going to formalize the problem based on formalize the optimization problem based on the models given to us. All right, so that's it for me. Please let me know if you have any questions. Thank you.